So our third speaker today is Uwe Simm from Cadence. He's an architect at Cadence. He works as a solution architect for the Cadence Verification Division with almost 20 years experience of design, implementation and verification of complex chips designs in various companies. He is currently focused upon verification efficiency and UVM system Verilog and has been contributing to the development of UVM since the UVM 1.0, I think. And the title of his talk is Common UVM Register Model Issues and Pitfall. And he's in Munich today from Germany. Over to you, Uwe.
Hello, hope you can hear me. Greetings from Munich. This is Uwe speaking. So I want to show you some of the issues around the UVM register models. Okay, here we go. All right, so first of all, let's start a little bit with presentation focus so that we know what we're talking about. So first of all, UVM Reg is one of the major building blocks in UVM land, and it has been used in various projects. And actually, as long as I remember, I can't really remember of a project which does not have registers in it. So it's one of the key elements in UVM. And just that you get an understanding how big it is in size, it's about half of UVM is UVM Reg code. Currently in IEEE is about 16K lines versus 36K lines of all of UVM. So here we are really talking about something which has a lot of functionality and a lot of code in it. So if we talk, let's figure out something. UVM Reg is typically fine if you deal with let's say what I call a standard stuff. So means byte and word addressing, static addressing models. So you're not changing anything in the addressing modes. You're not bringing in mode-dependent registers and stuff like that. So typically, when UVM Reg is fine, this is what I call module level usage. So basically, a small little bus going to a module, and basically you're reading and writing some of the registers. All of that is standard usage, and that's running fine. However, there are known issues, various known issues. There are drawbacks which are known, especially on the subsystem and interconnect and system level, which you should be aware of, because in case you're going there, you're likely to face problems. And today's talk, I just wanted to highlight some of the issues so that you're not blindly running into them, because some can be worked around, but some cannot, and you probably would have a hard time in that case. In any case, the presentation is neither a full list or comprehensive list, or does not intend to be basically the full universe of all the issues. It just gives you some heads up. If you want to see basically concrete issues filed with the working group, you should be heading over to that URL to look at the issues. If you're having issues, you can file them there, or you can search if the issues are known. Some of the conceptual issues are unfortunately might not be filed there, but that's the official point of contact, where you basically can search and find issues. Now, first of all, let's have a look at some of the structural or conceptual issues. To me, these are issues which are pretty hard to fix in the current code base. So these are not simple bugs where you just change a line of code or add something here and there. These are things which are kind of pretty hard to address in the current infrastructure. So the first thing, and I mentioned that already, that the current UVM Reg is not really data pathware. It's using a very simplistic and static hierarchical addressing model. That means you're not really having remapping support. You're not having support for bit steering and unpacked addressing. essentially all the nice things, if you're coming from IPExact, I mean, really full IPExact, not just a single component. If you're coming from the real IPExact with all the data routes and so on, all of that cannot really be mapped into UVM reg models. The next issue I'm seeing very often is compiler memory. It's very compiler memory intensive, especially if you go for subsystem. You know, everything is fine if you just talk about 50 or 100 or 1,000 or 5K registers, everything is fine. But once you go to 10K, 15, 20, 25, 50 or whatever, then things really get difficult, because every register or every map is a class type which derives from a UVM object, actually a fat UVM object. And in the end, also the field instances are class instances, which are in the end also derived from UVM object. So it's a problem in terms of turnaround time, so compile and elaboration time, and it's also a problem in terms of memory footprint at runtime. You know, the bigger you go, the more it will add. The next issue, which might not be really, you might not be aware of that, is that the register arbitration is actually happening at the highest level. When I say highest level, I mean on the access level of the register and not on the bus level. What I mean is that you could write a register in two different threads from two different agents. You write a single register, you call register.read or register.write, and the arbitration of that access happens on that call directly, and not on the bus. So the bus is not arbitrating, the call is arbitrating that for you. That means you cannot cause the bus doing arbitration for you, which essentially leaves you in a verification hole. So if you want to verify that the bus performs arbitration for you, then UVM reg won't do that for you because of the embedded arbitration scheme for the registers. And if you build subsystem system things, you will see that there's a lot of mix-up between the elements. So on one hand, we have instances. So elements you can instantiate where the focus is more like you reflect something like the RTL structure. So this is something like blocks and registers. So basically a block, a UVM reg block is something which maps to a kind of a component, and the register maps to a register instance. A memory maps to a memory instance, which is kind of a containment thing. It's like it maps to RTL structure. And on the other side, you have something like a map. A map is something like an addressing element. Unfortunately, the two things are mixed, and there are several issues and limitations how the two things can be used together, and how you can plug them together. That's not really sufficient if you go to system level usage. Another thing is, and we've seen that a couple of times, that there is no real separation of what I call a view, basically how you interpret the fields of a register or how you interpret the bits of a register. Is this one field or is it two fields? Is it read only or write only? And basically where the bits are stored. This typically ends up in registers which refer to typically named as mode-dependent registers. So there's a mode flag, and the mode flag defines if you see this layout of the bits or if you see that layout of the bits. Today you implement that with some workarounds. That you instantiate two registers and try to flip between the two, but it's more a manual thing what you can do. But there's no general way of looking at that. There's also no general way of dealing with indexing. Indexing of registers is a kind of a general capability. As of today, in UVM Reg, there's only one way of indexing things, which is indexing a set of registers by a register itself. But there's no indexing of blocks by a field, or no indexing of fields by a field. So there's also missing a generalization. That typically comes to play if you have a lot of repeated structures where indexing is used a lot, especially for channels and stuff like that. It would be very useful, and such a generalized structure is something UVM would be benefiting from. Now let's take a look at some of the SOC and interconnect scenarios. I already mentioned there's no dynamic routing model in contrast to IPExact. So there are no data routes which change over time. If you generate from most of the generators, all of them, they cannot cope with that dynamic model where the addressing changes over time. All you can accomplish today is, I think you can move an offset of a register block or register file, but that's it. But you know, other things they simply won't work, and you just need to compare IPExact compared to what UVM gives to you, and you see that there's a big gap. If you're not looking at IPExact, then obviously you might not see that problem. But if you come from IPExact, then a lot of things are there. Now, in more detail, if you look at addressing, you probably, if you're in UVM Regland, you probably have seen that you cannot have a map which is basically a map cannot have multiple parents, so you cannot really reuse a map. I just copied one error message what you would be seeing then, and that's actually despite of the UVM saying it can work with that, the implementation does not allow you to do that. So if you think of reusing your map, that won't work. So you have to copy all the memories and all the registers manually to a new instance of the map, which is not nice. Also, an underlying limitation is that you cannot add a register multiple times to the same addressed map. So in case you say, I just need one map, I do not need a hierarchical map, I just add in my system map, I add each of the registers one by one in all the places I need, that won't work. So you can only add one register instance once to a map, even if they're sitting at different addresses. I think you won't be even seeing a warning or an error message. It just happens due to the internal infrastructure. You cannot connect maps from different blocks. So if you have a UVM Reg block which contains a map, you cannot connect that map, which is an addressing thing, to basically to the addressing of some other block. So that's one of the breaks I mentioned earlier. This is where basically the boundaries of the component, the instantiation or the encapsulation, the instantiation thing breaks the addressing scheme. So addressing to me should be, let's say, kind of independent how you instantiate your models. And especially if you're working with addressing schemes which involve multiple layers of maps, and especially if they involve different properties or changes in properties of the n bytes. So basically you're changing the bus width over your layers, you're changing bit steering and unpacking, you're changing endianness, or you have multiple data routes, then unfortunately I have to tell you that the addressing most likely is broken for you. So if you I'm muted. Okay. I hope I still talk. So we fixed a couple of issues in the addressing scheme, especially for IEEE. So be aware that if you're having, buses, layered systems, then addressing might be broken for you in earlier versions of UVM like 1.1 and 1.2. Some of the other limitations. One limitation which might affect or might not affect you, so the address unit in bits must be a multiple of 8. So you cannot have a 7 bits bus or 5 bits bus. It has to be 8, 16, 24, 32, and so on. Other things won't work with UVM Reg. If you instantiate memories, then the word width of the memory has to match the width of the enclosing map. So you cannot have a 14-bit wide memory in a 16-bit wide map. This won't work. We have this whole block of lock model. Locking the model is some very strange operation, because lock model is not doing really any functionality. It's not adding any functionality. All it does is some caching, and unfortunately, this caching and checking prevents some of the things you could do. And unfortunately, some of the checks are actually even wrong, which even prevent further things. So lock model is a strange beast. In UVM IEEE, you at least have a chance. You at least have a chance to unlock your model, do some changes, and then relog again. In earlier versions of UVM, if you build your register addressing tree, you lock your model, then basically you locked it forever, and there was no way basically to change anything in the topology of your model again. Some more limitations. So registers cannot be at the same address, even that their fields do not overlap. So you cannot have a register at address 0 occupying the first 8 bits, and basically another register sitting at address 0 occupying basically the bits 7 to 15. So even if they do not overlap, it won't work. The exception here is a read-only, write-only pair at the same address, which is hard-coded in UVM. Wide memories with a smaller data path than the bus. This is also something which won't work. Some of the unexpected stuff you might have seen already. So if you're using mirror, be advised that mirror just conflicts with the explicit prediction, and the explicit prediction is either the standard mechanism, but especially it's used with pipeline BFM. So mirror won't work there. When I say it won't work there, it means you would see the accesses, but you would not see the outcome. You will not be seeing the results in your memories reflected. Then the mirror, if you say do a mirror and check, this might not be checking. Because there are two settings which influence the register map checking, which is basically a setting for the mirror and the register map. And there are several checks wrong, and especially if you construct your blocks, your maps, if you construct it manually or you need to do something special, you will be seeing all of that kind in when you're trying to construct and build it up. So be aware that quite some things are not in shape there. But that's it for kind of for the scary stuff, and I'm just moving for the summary. So in terms of summary, UVM Reg is good for standard or module level use models. It has been used successful, and it's doing its job there. No big deal. If you go for system, subsystem, interconnect use models, it might be very limited what you can accomplish. It might require extensive workaround if it's possible. And especially you need to be careful when you have multiple data routes. If you have dynamic data routes, multiple ports where transactions start, and if your data routes involve addressing or property changes, so multiple layers of a bus, multiple multiple bus widths and stuff like that. There are several bugs open, enhancements open in the IEEE to address the conceptual stuff, and in the working group to address the issues. Unfortunately, from my point of view, they are not just cosmetic changes. So some stuff has to change, and these are not just one-liners to change. And with that, I'm at the end. So if we just have time for questions, I would be open to answer.
Okay. Hi, Uwe. Thanks. Hi, thanks for the presentation. Unfortunately, you've run up right to the end, so we haven't got any time for any questions, unfortunately. But thank you for the presentation. Thank you.